Now we're going to talk about loudness of sound. Imagine I clap two blocks together. The sound wave is going to move out in all directions. As the wave moves out, the energy spreads out over a greater area. I know that looks like a circle, but it's actually a sphere. My ear is going to intercept some of this sound. How much depends on the value of R, the radius of the sphere that the sound spreads out through. Now you might wonder how much energy is going to enter the ear. Well, if you're going to talk about energy, you can just wait there and have more and more energy enter your ear if this was a continuous sound source. So we don't really want to talk about energy. We want to talk about energy per time. That's the power. That's the rate at which the energy is entering the ear. So if this is some sort of continuous sound source, like a loudspeaker, then we're going to talk about the power output of that speaker. That power is going to be spread out over a surface area, which is what we call intensity. And the area is 4 pi r squared, because that's the area of a sphere. So let's say the sound source continuously produced 1 watt of power. We were 1 meter away from that source. Then we would plug 1 watt here, 1 meter here. We have to square this, and we get 0.0796 watts per meter squared. Let's see what happens to the intensity if we move the ear out to 2 meters away. We still have 1 watt flowing out, but we're at 2 meters away. We get 0.0199 watts per meter squared. Now you can go back and do all the math again, or if you realize you've just doubled the radius and it's squared, then this number has to be 1/4 of this number. Now what would happen if we went to, say, 10 meters away? Well, we have to square that. It's going to be 1/100th of this value. And what if I went 10 times further? We're at 100 meters away. Well, that's like being across the parking lot at the school. If you had somebody playing a car stereo and you were across the parking lot and it was a quiet day, you'd probably be able to hear that. In fact, you could probably hear it even further away. In theory, you'd be able to hear it at 1,000 meters away. Well, you can't normally do that because there's background noise. You're going to hear the birds and the wind, and you're going to hear the cars going by. But if you had absolutely no noise at all, you'd still be able to hear this. Please take a look at the exponent here. This is way, way smaller than this. And it turns out our ear can handle intensities much greater than this, and even much smaller than this. So we have a very wide range of values for intensity that our ear is able to deal with. Think about this. If you were standing really close to, say, a lawnmower, you can handle that. And if you were standing far away from, say, somebody just talking to you, you can still hear them. So our ear is really designed to work with a very wide range of intensities. Well, it turns out they've measured people with headphones and special electronic equipment, and they found that the quietest intensity that a person with good hearing can have is 1 × 10⁻12 watts per meter squared. We call this I naught. Now, that doesn't mean 0 meters away from something. It's the quietest sound that you can hear. So how do we determine loudness? We use something called the decibel scale. This is how we calculate decibels. That's the loudness in decibels. We take the intensity that we're listening to and compare it to the quietest sound that we can hear. That's called the relative intensity. We take the log base 10 because the ear is not a linear device. If you double the intensity, it does not sound twice as loud. It only sounds a little louder, not much at all. So we're going to see what that works out to when we do the decibel calculation. You multiply by 10 to take bells and turn them into decibels. So take this intensity and divide by the quietest sound that we can hear. You're going to get a very large number without any units. Those units cancel with those units. Take the log of this number, base 10, times 10, and you now have 109 decibels. We'll put this right here. Well, let's do a few more of these. If you take this intensity and divide by the quietest sound we can hear, run it through the calculations, we get 103 decibels. Now notice, the intensity has gone down by a factor of 4, but this has only gone down by 6 decibels. It doesn't seem like very much. Well, now look what happens when we go to 1/100th the intensity. We've gone down by 20 decibels. Now we're at 1/10,000th the intensity, and we're down to 68.9 decibels. We now have a millionth of the intensity, and we're down to 49 decibels. So as we can see, the ear is not a linear device. This is designed this way so that we can deal with very large intensities and very small intensities. And what if we were listening to the quietest sound we could possibly hear? You'd have 1 times 10 to the minus 12th divided by 1 times 10 to the minus 12th watts per meter squared. And when you do that, you get 1. You'll have 0 decibels. That's the quietest sound you can hear. It's not that there's no sound, it's just the quietest sound you can hear. And everything is compared to that. So as we go up the scale, we have quiet, very quiet talking here, let's say. Maybe this is standing next to a lawnmower. And then maybe you have the rock concert here. At 120 decibels, your ears are really going to start to hurt. Anything up here, you better watch out. You could break your eardrum. So what's going to happen to the loudness if the intensity is cut in half? Well, just to keep things simple, let's just use 1 watt per meter squared up top. Do the math, you get 120 decibels. Now we'll cut it in half. We get 116.99. Let's cut it in half again and see what happens. I get 113.98. We'll cut it in half one more time, and we get 110.97 decibels. So what's happening every time we cut the intensity in half? We're losing 3 decibels every time, 3.01 to be more precise. Works the same way if we double the intensity. If we double the intensity, we're going to gain 3.01 decibels every time. So let's say you're standing over here listening to a stereo speaker and you hear a certain amount of decibels. We plug in a second speaker, identical. We've now doubled the intensity that you hear. But what happens to the decibels? It's only 3 more decibels. It takes a lot to make something sound a lot louder. If you asked somebody in an experiment, is it twice as loud? They'd say no. They'd say it's a little louder. You would have to have an increase of about 10 decibels for somebody to perceive that they're hearing twice as loud. Let's take a look at a graph. What if we tried to plot the loudness versus the intensity? It's a logarithmic function, base 10. This is the value of I naught. It gives us a value of loudness of 0 decibels. If I was at twice I naught, the quietest intensity we could hear, what would be the value of the loudness? We'd be at 3 decibels. If I was at 4 I naught, I'd be at 6 decibels. Well, wait a minute now. I'm only up to 4. If I was up to 10 times I naught, then I'd be at 10 decibels. Oh my gosh, I'm going to have to go really, really far to start getting 40, 50, 60 decibels. That's the idea of the logarithmic function. Our ear can handle very low intensities and extremely high intensities. We'll just make a chart because it's not going to fit on the graph. If we have I over I naught is 1, we have 0 decibels. At 10, we have 10 decibels. At a ratio of 100, we're at 20 decibels. At 1,000, 30 decibels. So if I wanted to have 30 decibels up here, I'd have to go out to 1,000 times I naught. Do you get the pattern? If we multiply the intensity by a factor of 10, the decibels go up by plus 10. That's the idea of a logarithm base 10. So how many times more intense is 40 decibels than, say, 30 decibels? Well, it's 10 times the intensity. How many times more intense is 40 decibels than 20 decibels? Well, it's going to be times 10 again. That's 100 times. So 40 decibels versus 10 decibels is 10 times 10 times 10. It's 1,000 times. All right, here's a practice problem. Let's say we were 4 meters away from a speaker and we were listening to 80 decibels. Could you find out the power output of that speaker? So we plug 80 decibels into the equation. We divide by 10. We have 8 bells now. How do I get I? I have to remove the log. How do I do that? By using a base of 10. That will cancel the log. If I do that to this side, I have to do it to that side. So we say 10 to the 8th is equal to I over I naught. And I equals 10 to the 8th times I naught. And we get 1 times 10 to the minus 4th watts per meter squared. Ah, but that's not the power, is it? Remember, intensity is power per area. And we're assuming the sound spreads out in all directions, 4 pi r squared. That's not exactly true in real life. It's more directed to the front. But if you stood behind the speaker, you'd probably hear it too. So let's just assume it's a point source. We'll put 4 meters in for the radius. Wow, that's a small number. If you know anything about stereos, that's a very small number. Many speakers have ratings of 100 watts or 200 watts. Why are we having such a small amount of power? Well, one, remember, we're not at the loudest thing that you can hear, but that's only part of the story. The real story is that we don't need a lot of power to hear sound. When you look at stereo ratings, they're talking about power input. The power output is what you hear. And the power output doesn't have to be very big to get a good sound. So most of the energy that we pump into our speakers is going to waste heat. The wires, the magnets inside here get hot. Now, don't forget to practice these problems on the worksheets.